Alright, looks like we are live. Let's continue. Let me open the table of content first. Okay, we are on chapter 15. If I remember correctly, we are on summary section here. Let me check that. We already take a look at this. We already take a look at this too. Okay. We already take a look at this too. Right? Oh, or maybe on this one. Hardware support summary. If I remember correctly, we already take a look at this. Right, the rack or something like that. Okay. Privilege mode. Dynamic relocation. Okay, we already check that out too. Operating system issue. Right. With variable size address space. Life is more complicated, but we will leave that concern for future chapter. We have to check this out. Okay. Operating system responsibility, okay. To check that out too. Okay. Limited direct execution. Oh, I think we already checked this out too. Right, this is the one with no program yet, only during boot time, something like that. The first figure show what the operating system does at boot time to ready the machine for use. And the second shows what happened when a process A, start running. Not how its memory translation are handled by the hardware with no operating system intervention. At some point, middle of second figure, a timer interrupt occurs and the operating system switches to process B, which executes a bad load to an illegal memory address. At that point, the operating system must get involved, terminating the process and cleaning up by freeing B's memory and removing its entry from the process table. As you can see from the figure, we are still following the basic approach of limited direct execution. In most cases, the operating system just sets up the hardware appropriately and lets the process run directly on the CPU. Only when the process misbehaves does the operating system have to become involved. Right. I'm kind of curious about the timer interrupt. Like, what is it called? Is the timer interrupt gonna interrupt every process during X amount of time? Maybe. Let's say I'm doing process A, and then suddenly the time for the timer interrupt, what is it called, is fulfilled, I guess. Basically the timer interrupt occurs, right? And then we are gonna switch to another process after that. Is that mean that we, what is it called, switch back and forth between process A, between each process with the specific amount of time? Is that it? Yeah, let me do we switch process constantly switching the process every time the timer interrupt occurs. Let's say the timer interrupt is every 5 milliseconds. Are we gonna switch the process every 5 milliseconds? Is that it? Yeah, I'm still not sure yet. Maybe we will find that in the future chapter, especially during concurrency here, right? The second piece. So for now, let's continue into the summary here. In this chapter, we have extended the concept of limited direct execution with a specific mechanism used in virtual memory known as address translation. Okay. Limited direct execution with specific mechanism used in virtual memory known as address translation. With address translation, the operating system can control each and every memory access from a process, ensuring the access stay within the bounds of the address space. Key to the efficiency of this technique is hardware support, which performs the translation quickly for each access, turning virtual address, the process view of memory, into physical one, the actual view. Okay. Let me check again. With address translation, the operating system can control each and every memory access from a process. Okay. Ensuring the access stay within the bounds of the address space. Key to the efficiency of this technique is hardware support, which performs the translation quickly for each access, turning virtual address, the process view of memory, into physical ones, the actual view. All of this is performed in a way that is transparent to the process that has been relocated. The process has no idea its memory references are being translated, making for a wonderful illusion. Right, this transparent in here means invisible, so the process didn't know what's going on. Not really, what is it called? About the open, right? Sometimes transparent can also translate to openness or something like that, but not in this case. It is quite the opposite. Transparent in here means invisible to the process, and then the process has no idea what's going on with the memory it's used. We have also seen one particular form of virtualization known as base and bounds or dynamic relocation. Base and bounds virtualization is quite efficient as only a little more hardware logic is required to add a base register to the virtual address and check that the address generated by the process is in bounds. Okay. Wait, let me check figure 15.6 first, I guess. Limited direct execution, dynamic relocation at runtime. So we run some program here. Okay. Here, operating system at run. To start process A, allocate entry in process table, allocate memory for process set. Okay, allocate memory for process. Okay, there is a process table, and then we allocate some entry in the process table, so we keep track of the process in the process table, I assume, and then allocate memory for process. Okay, this is the interesting one. I mean, with this base and bound mechanism, I'm assuming we allocate everything from the get-go. Again, something like this. We allocate a contiguous memory, maybe something like that, which means there is some case where the memory is allocated but not in use. So we take up the memory space, but it is not actually in use. Maybe something like that. And yeah, from this, what is it called? From this illustration, it looks like contiguous, right? So it is side by side, maybe something like that. Okay. Yet, wait a minute. I think if we are doing this like doing it like this, the problem is that what happens when the current memory block is not enough to store what is it called? To store the total allocated space here. Yeah, that is interesting, I guess. Again, like what the books say here. With variable size address space, nav is more complicated. In this example, we assume that the size the size of address space is smaller than the size of physical memory, and its address space is the same size. So there's no variation for the address space. Maybe something like that. Okay, wait, let me check this again. That is part of the allocate memory for process, and then set base or bounce register, then return from trap into A, right, restore register of A, move to user mode, jump to A's initial program counter. PC in here means program counter, if I understand correctly. And then process A runs. We fetch instruction, translate virtual address translate virtual address, and then perform fetch. Execute instruction. Oh, okay. So we first fetch the instruction and then translate the virtual address of those instructions. Perform fetch to get the, what is it called? To get the data from the virtual address, and then execute the instruction, I guess. So yeah, I'm assuming instruction in here means, what is it called? Maybe something like a function. You know, function also save in the memory, right? So we fetch the function virtual address, and then we are translating that virtual address, and then we fetch the, what is it called? The function instruction, the instruction inside the function, right? And then executing those instructions. Maybe something like that. The, what is it called? The analogy that I use here is the function to make things easier to imagine, I guess. I mean, if we call this instruction and then execute instruction, it's kind of ambiguous. Like, what instruction are we talking about here? But again, my analogy might be wrong. Just something to keep in mind. If explicit load or store ensure address is legal, translate virtual address, perform load or store, it runs. Okay, I'm assuming the store path in here is like assigning a value in the variable. You know, the variable is some sort of data storage, right? We save the data in the variable. So maybe that is the part of explicit store here. And then when we load, I'm assuming it means something like using the variable, or maybe a pointer when we are dereferencing the pointer value, right? Maybe it can also be considered as explicit load. and then can ensure a trace is legal. For example, if we are trying to dereference null pointer or something like that, it is illegal address, I guess. We cannot do that, so we will get some exception when we are trying to reference null pointer to dereference null pointer. And then if it is legal address, translate the virtual address and then perform load or store. A runs timer interrupt. Right. This is what make me curious. Like, if we have a dedicated hardware for the timer interrupt here, are we constantly shifting between process, like every 5 seconds switch process, every 5 seconds can switch process, or maybe every specific amount of millisecond, like 5 milliseconds switch process, 5 milliseconds can switch process. Yeah, that's what I'm still not sure about the timer interrupt here. Again, maybe we will understand better on the concurrency piece, right? The second piece of the book. Okay, move to kernel mode, jump to handler timer, decide stop A, run B, call switch routine, save register A to process track A, including base or bounds. Okay, I'm assuming we are saving this in the kernel stack, but again, what is it called? How many memory do we have in the kernel stack? Right? If we need to saving the register of the process in the kernel stack. Yeah, I'm still not sure. There is something to check out, I guess, if I didn't forget. Okay, let me what is it called? Let me take notes. How many memory do kernel stack has, so that we can save the register from different process, from multiple process, or something like this. And then we are restoring register B from process structure B, including base or bounds, and then we return back to the user mode, restore register of B, move to user mode, jump to B's program counter, process B runs, execute pet load. Okay, load is out of bounds, move to kernel mode, jump to trap handler, handle the trap, decide to kill process B, deallocate base memory, free base entry from the process table, I guess. Free base entry from process table in process table, right? Okay. And that is the limited direct execution dynamic relocation at runtime. Okay. Let me reread this. We have also seen one particular form of virtualization known as base and bounds or dynamic relocation. Base and bounds virtualization is quite efficient as only a little more hardware logic is required to add a base register to the virtual address and check that the address generated by the process is in bounds. Base and bounds also offer protection. The operating system and hardware combine to ensure no process can generate memory reference outside its own address space. Base and bounds also offer protection. The operating system and hardware combine to ensure no process can generate memory reference outside its own address space. No process can generate memory reference outside of its own address space. Protection is certainly one of the most important goals of the operating system. Without it, the operating system could not control the machine, right? If processes were free to overwrite memory, they could easily do nasty things like overwrite the trap table and take over the system, right? So the isolation part, I guess. Unfortunately, the simple technique of dynamic relocation does have its inefficiency. For example, as you can see in figure 15.2, page 5. Where is it? This one, okay. Right. What is it called? The representation of a contiguous address space in the memory, I guess. Single allocated process. Okay, let's go back to the summary. Okay, in figure 15.2, page 5, the relocated process is using physical memory from 32 kilobyte to 48 kilobyte. However, because the process stack and heap are not too big, all of the space between the two is simply wasted. Right. Okay. From this figure 15.5, right, it looks like this is a contiguous memory which is side by side, right? And there is a part where it is allocated but not in use. It is again wasted, right? We didn't use this memory allocation, but it is what is it called? It still have the use status. So that kind of wasted. Guess that's the word. Okay. All of the space between the process stack and heap is simply wasted. This type of waste is usually called internal fragmentation. Oh, okay. As the space inside the allocated unit is not all use that is fragmented and thus wasted. Oh, okay. In our current approach, although there might be enough physical memory for more process, we are currently restricted to placing an address space in a fixed size slot, and thus internal fragmentation can arise. Thus, we are going to need more sophisticated machinery to try to better utilize physical memory and avoid internal fragmentation. Our first attempt will be a slight generalization of base and bound, known as segmentation, which we will discuss next, right? In this section, I guess. Chapter. In the chapter 16. Okay, let me read the footnote here. A different solution might instead place a fixed size tag within the address space just below the code region and a growing heap below that. However, this limits flexibility by making recursion and deeply nested function calls challenging, and thus is something we hope to avoid. Okay, this one, the footnote from this one, internal fragmentation can arise. Okay, this is the reference on dynamic program relocation. This paper is a nice summary of early work on dynamic relocation, as well as some basic on static relocation. Relocating loader for Microsoft DOS.exe executable file. Oh, okay. Wait. An example of a relocating loader for Microsoft DOS. I'm assuming MS in here means Microsoft, I guess. Not the first one, but just a relatively modern example of how such a system works. Okay, how such a system works. The protection of information in computer system. Alright, from this paper, the concept of base and bound register and hardware interpreted descriptor appear apparently independently between 1957 and 1959 on 3 projects with diverse goals. Oh, 3 projects with diverse goals. Interesting. At MIT, McCarthy suggests the base and bounds idea as part of the memory protection system necessary to make time sharing feasible. IBM independently developed the base and bound register as a mechanism to permit reliable multiprogramming of the threads. Computer system at Burroughs or Barton suggests that hardware interpret descriptor would provide direct support for the naming scope rules of higher level language in the B5000 computer system. Oh, interesting. We found this quote on Mark Smotherman's school history page. See them for more information. Okay. System call support. Oh. Okay. A neat history of system call support. Smotherman has also collected some early history on items like interrupts and other fun aspects of computing history. See his webpage for more detail. Okay. Is it also consists of the timer interrupt too? The history about timer interrupt, maybe something like that. Efficient software-based fault isolation. A terrific paper about how you can use compiler support to bound memory reference from a program without hardware support. The paper sparked renewed interest in software technique for isolation of memory reference. Okay, answer to footnote. Is there anything other than a fog that can be black? By Wachuma Muanchohi. Okay. Amazingly, this enterprising reader found the answer via Google's Ngram viewing tool. Available at the following URL. Okay. The answer, thanks to Mr. Wanjohi, it's only since about 1970 that Wreck Havoc has been more popular than Wreck Vengeance. Is that how you pronounce this? Most likely not. Wreck Vengeance in the 18,000. Yeah, the word work was almost always followed by his there vengeance. Apparently when you wreck, you are up to no good, but at least wreckers have some option. Yeah. At least wreckers have some option, right? Okay. Homework simulation. The program relocation.py allows you to see how address translation are performed in a system with base and bounds register. Okay. Alright. I guess we will explore this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.